Okay, so we lost a little time, but it's nothing too bad. So we've got, so now we're doing this cylinder. Okay. And what direction do you think the electric field's going to go? So lambda is charge over length. Well, I mean, again, kind of from symmetry, we kind of think the electric field should point straight out in all directions. Right. So if I think about finding the flux through that cylinder, well, if I'm standing on the side of the cylinder, like right here, then the electric field and I am in the same direction. So it's cosine 0, which is 1, right? If I'm standing on the top of the cylinder, well, the electric field's going this way. I'm standing this way. So we're perpendicular to each other, right? So cosine of 90 is 0. So when I find the flux, well, the top and bottom aren't going to give me anything because I'm perpendicular to the field. But I will get something from kind of the side part of the cylinder, right? So the flux is going to be the electric field times the, well, in math we called it the lateral surface area of the cylinder. But all that means is the area of the round part, but not the area of the top and bottom, right? Which, what's the area of the round part of a cylinder? Well, it's, if you imagine snipping the cylinder and rolling it out to make a rectangle, it's, the height would be the height, the length would be the circumference of the bottom, so it's E times 2 pi r times however high we cut out for our cylinder. On the other hand, how much charge is inside? Well, lambda is the charge per unit of length. So, it's Q over epsilon naught, which the charge would be lambda times however much height we cut out, because, yeah, height is how long we're cutting out, over epsilon naught. And so if I get the E by itself, well, the H's cancel. So I've got E is lambda over 2 pi r epsilon naught. So this is for an infinite line of charge. All right. Okay. And let me do one more. Oh, by the way, if I think about it whenever we get to the first test, I mean, there's possible I just don't think of this question at that time. But if I think to ask it, like my, hey, explain something to me, will probably be something along the lines of, intuitively explain why Gauss' law should be true. So that's what we've talked about today. FYI. All right. Let's go and do one more, and then we'll call it good for today. We'll try to do it. Dude, I just gave you the answer. You don't have to say the whole thing. It's like, oh, it's water flowing in should be the same as water flowing out, unless you've got like a sink pouring in or you got a drain pouring. I mean, that's basically what I'm looking for. All right, so parallel plate capacitor, that's a fancy name for, you've got two plates that are really, really close together, and one has a positive charge on it, one has negative charge. And the charges are the same, but just one's positive, one's negative. All right. If I think about that guy, it's, well, a couple things are, I'm not going to, I don't want to take the time to explain it. Okay, so I'm going to just tell you, on the outside, it's basically 0. On the inside, well, I'm going to draw my little Gaussian surface. I'm going to draw a cube. There's my cube. I know the flux through, so I feel like the electric field should just go horizontal, right? Basically the same reason it did for the infinite line, right? So the flux through the top and the bottom are 0 because I'm standing the wrong direction. The flux through this side over here is also 0 because my electric field is 0 out there. So the only part that's going to matter is the flux right there. So the only contribution to phi is that surface right there. So that means my flux is going to be whatever my field is times the area of that surface. Right? And I guess I should have said something about this. Let's say that the plates have surface charge density sigma. So this would be this guy's charge over area. Right? I mean, it's a plate, so you would want, like the line you think about, oh, it's got a ton of charge that goes forever, but you think, oh, well, we could talk about charge per unit of length. Same thing, if these plates go forever, they should have a ton of charge, but we should be able to talk about how much charge they have per unit of area on the plate, right? So on one hand, phi is E times area. On the other hand, the total charge, well, it would be the charge per unit of area times the area. So that's my Q over epsilon naught. And happily, what cancels out? The areas. So E is just sigma over epsilon naught inside a parallel plate capacitor. Which shows you why they're so useful. Notice that it's constant. So like our, when we did the electric field of a point, it had a 1 over r squared in it. When we did the electric field of a line, it had a 1 over r in it. This thing doesn't actually depend at all on where I am between the two plates. Here's my plates. If I'm here, if I'm here, if I'm here, if I'm here, doesn't matter. Electric field's the same everywhere, which is why parallel plate capacitors are so incredibly useful in real life. So that, in real life, this is a very useful way to make a constant electric field. And you get the extra bonus that not only is it constant in the middle, it's 0 on the outside. So this gets used in a lot of electronic stuff because, hey, this way you can build a little thing to have an electric field where I need it, and it's not going to screw up with all the circuitry around it. So it's good. All right, so that's kind of just examples of how you can how you can use Gauss's law to find electric fields. I mean, another one we could do, I don't want to do it right now because we're out of time. But like, for example, say instead of having a point charge, let's say you had a solid sphere that was charged. Well, if I go way out here, I mean, if you think about it, the shape or whatever, the electric field lines are going to still go straight out. They're going to be on spheres, just like they were for the point. So if I'm way outside the sphere, it should be exactly the same. It should still be the charge of the sphere over 4 pi epsilon naught r squared. What would change is if I wanted to know, hey, what's the electric field inside of the sphere of charge? And then it would depend on how much of the total charge is actually inside here. And so you can do that one with Gauss law too, but we're kind of out of time, so we might not do it right now. You can do it as part of your homework. Because you're confident in yourself, aren't you? And you'll come visit me if you're not. So, okay. Everybody pretty happy with Gauss law?
Yeah.